Hello guys, nice to see you. Good afternoon.
Good afternoon.
Hello.
Hello.
Hi, nice to see you.
Hello.
Hello everyone. So, last time we considered time-changing magnetic field flux, which creates, like induces electric current in closed conductive loops. Also consider this so-called Lenz's law, which defines the direction of these induced currents. So today we will focus more on induced electric field. So it's a bit different from electrostatic field because electrostatic field is created by stationary charges. However, this induced electric field does not have sources as electrostatic. We don't need to have any electric charges in order to create this induced electric field, which originates from the changing magnetic field flux. And obviously, it will possess different properties than electrostatic field. So we will focus today more on these aspects and features of induced electric field, which are different from electrostatic field. And also we'll consider certain applications of this effect of induced current in and electromotive force. So where this effect can be applied. Obviously, the most widely established application is in electrical generators, where we convert mechanical work into electrical power. And that is the fundamental technology for all electric power, which we use in everyday life. So we will also discuss this electric current generation. We are rotating loop, like conductive loop in external magnetic field. Okay, let me switch to our slides. So as we mentioned earlier, we can relate some induced current and electromotive force with changing in time magnetic field flux. The thing is that in order to, so if we have this electromotive force generated in a closed loop, obviously we have some electric field induced also. And the key difference between electrostatic field and induced field that we don't have charges as source of this field. So let us consider some closed loop in the form of a circle in external magnetic field B. So the radius of this loop will be R. And we have magnetic field lines or magnetic field vector perpendicular to the plane of this conductive loop. And let us assume that this magnetic field is a function of time, so it changes with time. As a result, according to Faraday's law, there will be some electromotive force generated minus first derivative of magnetic field flux over time. If we consider some electric field, which is also induced around this loop, its orientation will be tangential to the conductive loop because this is the direction of motion of electric charges. So that's vector for electric field, and can put one more here. The work which has to be done in order to move a charge carrier all over this conducting loop should be equal to electric charge times electromotive force, like induced electromotive force, because of changing magnetic field. So in other way, we can express it via electric field. So we can consider electric force, which is exerted on a charge carrier. So it will be Q times E, like magnitude of induced electric field, times the circumference of this circle. So the total path of electric charge. So it will be 2 pi times R. So that is equal actually. So we have on one side electromotive force, from another side product of induced electric field and circumference of the conductive circular conducting loop. And we can express induced electric field E as induced electromotive force divided by 2 pi R. From other point of view, there is obviously an option to express it in terms of varying magnetic field flux. And since the reason for changing magnetic field flux is magnetic field, so also can consider specifically change of magnetic field in time. For instance, we can write that in our case, magnetic field flux will be equal to magnitude of magnetic field vector times pi R square, which is the area of the current loop. And electric field E will be equal to minus 1 over 2 pi R times, instead of epsilon, we substitute minus dFB over dt. So in that case, let's write it here, dFB over dt. So now if we substitute expression for FB, for magnetic field flux, we will get the following. So it will be minus 1 over 2 pi R then we have pi r squared dB over dt. It's actually first derivative of the function which describes magnitude of magnetic field versus time. So here we cancel out this pi, this r and square. So we get actually minus r divided by 2 times dB over dt. So that is the relationship between induced electric field and first derivative of changing magnetic field over time. To be a bit more general, since not always conductive loop will be in the form of circuit, and it's not always that we have uniform electric field, induced electric field. So to be more general, we can write that induced electromotive force can be expressed as integral, like line integral over closed current loop of scalar product, electric field vector, and ds vector, which is the displacement vector, small displacement vector along the closed loop. So taking this into account, we proceed further. So we remember electromotive force from one side, according to Faraday's law, is minus dFb over dt, and that should also be equal integral over closed current loop of scalar product E vector ds vector. Now, what is actually important to underline here, and this is already here written in this slide, what is fundamentally different between induced electric field and electrostatic field. Do you remember for electrostatic field, this integral over closed path in electrostatic field, what it's equal to? It highlights one of important feature of electrostatic field. We can write this integral E electrostatic, let's say static, times ds vector. This should be equal to 0. So it means that we have conservative electrostatic field is a conservative field, and then this integral over a closed loop is equal to 0. However, we see here that for induced electric field, which doesn't have charges like sources of this field and formed because of changing magnetic field in the vicinity to this point where we consider induced electric field, is not equal to 0, it's actually equal to minus first derivative of magnetic field flux over time. So it means that it's non-conservative field, and this is the key difference between induced and electrostatic electric fields. So that you should definitely remember. and understand this difference between these types of electric fields. Now let us consider some example when we can determine the magnitude of induced electric field next to some conductor with certain shape. In our case, we will consider a solenoid. So let us assume that we have some solenoid with electric, like time-dependent electric current flowing through it. I is a function of t. So here is the same current, I as a function of time. Let us assume that the radius of these coils, which form solenoid, will be capital R. Now let us first consider electric field outside solenoid, like induced electric field by this time-dependent electric current flowing through solenoid outside solenoid, and in next step we will consider inside solenoid. So first outside, we make such imaginary loop with radius R, and this radius is larger than the radius of the solenoid. So our goal is to get some function which will describe induced electric field as a function of position, this like radius as a function of position from the axis of this solenoid. So that is what we want to derive. So let's start from the first derivative of magnetic field flux over time, which will go through this loop marked with dashed line with radius small r. So in this case, it will be dfb over dt equal to minus d over dt, and here is magnetic magnitude of magnetic field vector times pi r capital square. So that will be total area which we consider. It will be a cross section of this solenoid. Why? Because magnetic field of a solenoid outside the solenoid is much weaker than magnetic field inside solenoid. So we already discussed this question, and its contribution will be negligibly small, so we can neglect this. So what will be the, we can maybe take out constants from this derivative. So it will be minus d over dt. And here, sorry, first our constants. Let's write it here. Will be minus pi times r square times db over dt. So we need to deal with the first derivative over time of this magnetic field, magnitude of magnetic field. Let us define what will be a magnetic field inside solenoid. We remember our previous discussions for the magnetic field inside solenoid, B is equal to mu naught. We assume that it's just empty space there. There's no any material inside, times N, which stands for density of turns per unit length of these coils of solenoid, and times current, which is a function of time. To be more specific, we need to define this function. And let's say we have mu naught times N times some I maximum times cosinus omega t. So that is how electric current which flows through the solenoid depends on time. So it's some periodic function cosinus omega t. And I max is the amplitude value, amplitude maximum value for electric current. So in order to get now this negative first derivative of magnetic field flux, which we want to get from here, we need to substitute this expression for magnetic field as a function of time, like actually here by taking first derivative over time. Maybe let me go to another slide because we'll be overcrowded there. So minus d f b over dt is equal to minus pi r squared d over dt. And here is our time-dependent function for magnetic field. It will be mu naught times n times I maximum times cosinus omega t. So here these three guys are constants, so we can take them out from the parentheses, like from the derivative will be minus pi r squared mu naught n I maximum times d cosinus omega t over dt. Derivative of cosinus omega t will be equal to omega times minus sinus omega t. So now if we take that into account, so we can write maybe here that this derivative will be equal to minus sinus omega t times omega, because we need to multiply by the derivative of the argument of cosinus. So it will be omega. And that's why we will get minus and minus will give us plus pi times r squared mu naught times n times omega times I maximum times sinus omega t. So now, when we know the negative first derivative of magnetic field flux through this dashed closed loop, which we consider around the solenoid with radius r, we can proceed to the next step. So the integral over this closed path for electric field times like dot product ds vector, assuming that we have a circular path, then it will be just E electric field, induced electric field times the length circumference of the loop, 2 pi r. And this should be equal, from previous discussions, it's equal to induced electromotive force, and induced electromotive force, according to Faraday's law, is negative first derivative of magnetic field flux over time. And we already know that it is equal to pi r square mu naught and omega I maximum times sinus omega t. So now we can express this induced electric field as a function of distance, like r, from the axis of solenoid. So E, when r is larger than radius of the solenoid itself, so in the external space outside the solenoid. So induced electric field will be equal to, we can rearrange a bit this, mu naught times n times I maximum times omega r square divided by 2r, and this multiplied by sinus omega t. Again, assuming that r is larger than radius of the solenoid. So in this case, we see this induced electric field outside solenoid as a function of time. And what is important, that if we pay attention on its dependence on distance from solenoid, we see that this distance, which is small r, stands in the denominator. So it means that induced electric field outside solenoid will be proportional to 1 over r, means we reduce magnitude of induced electric field when we go further from the solenoid, from the axis of solenoid. Now, let us consider the second case, when we have internal space of solenoid, how induced electric field will change there. So if r is smaller than the radius of the solenoid, then this first like negative first derivative of magnetic field flux should be equal to minus d over dt times magnetic field inside solenoid times y r square. So here the difference between the previous case is that we have here a small radius because we consider loop with the radius smaller than the radius of the solenoid itself. So previously we considered the whole cross section of solenoid and used capital R because our loop was larger than the radius, than the cross section of solenoid. Now it's smaller, so we need actually to consider the not area of whole cross section area of solenoid, but area of the loop, which is located already inside the solenoid. So that's why we have minus pi r square times first derivative of magnetic field over time. Taking this into account, we can write that minus dFB over dt is equal to minus pi r squared, like small r squared, mu naught times n as I maximum. Then again, derivative over time of cosinus omega t. And that is equal to pi r squared mu naught n I maximum times sinus. Sorry, I forgot. Here should be omega times sinus omega t. The same approach for integral over closed loop for electric field times ds vector, that will be in the case of small loop inside solenoid, will be induced electric field times pi r squared. And this should be, sorry, it's not area, it should be length 2 pi r. And this should be equal to this negative first derivative of magnetic field flux, which is pi times r squared mu naught n I maximum times omega times sinus omega t. So from here, we can cancel this r and this square, and also this pi. We can get the expression for induced electric field as a function of time inside solenoid. So that will be equal to mu naught times n, density of coils per unit length, times m maximum, I maximum, times omega, and here will be small radius, like actually distance from the axis of the solenoid to the point where we want to determine induced electric field. All this divided by 2 and multiplied by sinus omega t. So here we see, if we take a look on induced electric field as a function of distance from the axis of solenoid inside solenoid, it is proportional, linearly proportional to radius. So it actually will, induced electric field will increase as radius, like distance from axis of solenoid increases. But that, as we have shown previously, will happen only until we reach the radius of solenoid, capital R, and once we increase distance from the axis of solenoid further, then we will switch to another regime when induced electric field will reduce with the increase of magnetic, with the increase of distance, because it will follow different equation which was derived on the previous slide. So now I would like to focus your attention a bit on applications of this induced electromotive force, induced current. We are changing magnetic field And as I mentioned earlier, that is actually the most widely developed application is electrical generator. So let me share with you my screen. Yeah. So here on this slide, you can see an example of handmade generator for this, actually made for windmill. So it consists of two components. We need for every electrical generator, we need rotor. So this is rotor, which actually spins. It rotates. So some torque, mechanical torque is exerted on this part of the electrical generator. It starts to rotate it. So it means it starts to use some mechanical work in order to convert mechanical work to electricity. So it consists of many strong permanent magnets, which are placed at certain distance, which is equal to the distance between these coils on the starter. So this part, another part, which is stationary of an electrical generator, is starter. So not always rotor has permanent magnets and starter has wires. It could be different. We will consider like the case when rotor is actually a coil and starter will be permanent magnet. So they can be used in different combinations, but always we have some stationary and some mobile parts which are called rotor and starter. So what happens if you imagine putting this rotor over starter and start to spin it in close vicinity, there will be experience some change of magnetic field flux through these coils of copper wire because of moving these permanent magnets. So the faster this rotation will happen, the higher induced electric current and electromotive force will be collected at the terminals of all these coils connected between each other. So in such a way, you can convert mechanical work, which you, like some torque, which you collect from the blades of a windmill to electricity and then accumulate it or use for any purposes. So next slide here shows a bit different, more classical configuration for electrical generator. Here we have rotating current loop, like some wire coil, which is connected, which terminals are connected from this to this current collecting rings, and this coil is rotating in permanent magnetic field. So here we can call this permanent magnet as stator and this rotating current loop as rotor. So the electromotive force and also stands similar to induced electric current is such a periodic function, which means we have with such electric generator, we generate so-called alternating current. It's not DC current because it's not only changing in magnitude, but also changing in direction. So also in this particular case, we show electromotive force. So its polarity from positive goes to negative, then again becomes positive and negative. So this is a classical example of alternating current generator. If these rings, current collecting rings are modified, so actually it's called commutator, that in certain moment of time you can collect induced current or get induced electromotive force only to one of isolated summer circles of these collecting rings, then we can, by modifying this collector in such a way as shown on the image, when it consists of two halves isolated from each other, we can go from alternating current generator to DC current generator. However, it is still here time dependent electromotive force and also time dependent induced current. In order to make it more smooth and closer to DC, one option is to connect in parallel a capacitor, which will charge and discharge. So it will take some time to charge capacitor. So the voltage at the terminals of such generator will rise a bit slower. And then when electromotive induced force declines, the discharging capacitor will provide some residual current because it will be discharging. So it kind of will smooth these peaks and make less pulses of induced electromotive force and magnetic field. However, that's already an example how you can change the design of this electrical generator in order to go from alternating to DC current generation. So now I would like to come back to our slides and let me escape from this. And we will quantitatively analyze a bit this work of such electric power generator when we have a coil rotating in permanent magnetic field. So the flux through such magnetic field flux through such coil will be FB equal to magnitude of magnetic field times area of this current loop, which is wire coil rotating inside, times cosinus theta. So in this case, magnetic field is constant, area is constant, only this angle theta is changing. That's actually coming back to our previous discussion. There was a question how we deal with this time-dependent orientation. So that's actually the case when we consider this, because here only orientation of the current loop with respect to permanent magnetic field. That's the only time varying factor which causes change of magnetic field flux. So this angle theta we have to represent as a function of time. So that will be magnetic field times area times cosinus omega t, where omega is 2 pi times nu, frequency, how many revolutions per second this coil does. So if we want to determine the induced electromotive force, that will be minus n. So that is number of coils. Yeah, I think we can add this n here also. So that was for a single coil, but if we have just many coils which form this current loop, so it will be n times minus n times d here we already don't write derivative. It will be minus n times b times a, and because these are constants, and here will be d over dt cosinus omega t. So that will be plus already n times a b times omega sinus omega t. So here we get the maximum, so we can actually write it in a bit different form. So it will be epsilon maximum times sinus omega t. So this epsilon maximum, this is the amplitude value for induced electromotive force, will be n times a times b times omega. And obviously it will be some periodic function at the terminals of the current loop. If we have epsilon and time, so it's sinus omega t, so it will go from 0 and follow this sinusoidal law when reaching this maximum value epsilon maximum. What is important also to highlight that the frequencies is nu, which will be omega divided by 2 pi. For instance, in Kazakhstan, also all over Europe, nu is 50 hertz in the electrical system. In North America, like United States and Canada, this frequency is 60 hertz. So there is certain difference in these frequencies, but all modern and exploiting like majority of all electric power systems, only with very few exceptions, they are based on alternating current generators and alternating current. There are some special electric power systems based on DC current when we have constant voltage and DC current. However, this is more applicable to some specialized cases, but the majority of common use electric power systems, they are based on alternating current and on similar device architecture of electrical generators, which we consider during this discussion. So if you have any questions, you're welcome. We, like summarizing our discussion, we explain the difference between induced electric field and electrostatic field. So the fundamental difference is that we don't have sources of induced electric field. It originates from the change of magnetic field. And it is not a conservative field. So it's non-conservative field as opposite to electrostatic field because integral over the closed path of the scalar product of electric field vector and times the S vector is not equal to 0, but it's equal to first negative first derivative of magnetic field flux over time. And also we discussed the structure of commonly used electrical generators as the most widely established practical application of induced electromotive force and induced current in order to generate electricity and for different uses. So that is based on rotor and stator, means we have one part with which rotates, which transfers externally provided torque and converts eventually mechanical work to electrical current. And it's also all this generated current is induced current, which is because we have rotating current loop coils inside permanent magnetic field. So it's one of the common configuration for electrical generators. So this rotation provides time-dependent magnetic field flux, and we have shown quantitatively how we get the magnitude of induced electromotive force in this particular case. Okay, guys, thank you very much for attention.
Thank you. Have a nice day. See you later. Goodbye.
Yeah, see you on Wednesday. Bye-bye.
Thank
Take
you.
Bye.
Thank you. Goodbye.
Bye.